Okay, so let's start. So first, announcement. For the homework, we just put something called a LaTeX template on the course website. So basically, LaTeX is one way that you can produce nice PDFs, including a lot of math formulas and so on. Okay, it's a very convenient way to produce scientific reports and papers and so on. Okay, I don't know how many of you have had experience with that. You are encouraged to use LaTeX to produce your homework, and to make this easier, in case you haven't seen this before, we put a template on the course website, as well as how tutorial of how to use it. Okay, yes, all right. But you don't have to use it if you find that this is something that it's confusing for you. Okay, but you're encouraged to do so. All right. So last time we had an introduction of what this course is about, and we started to talk about analyzing time complexity of an algorithm. Okay. Now, so let me just first move to where we are last time. We ended with looking at some examples of nested loops. Okay. Now, one thing we said is that when you are given nested loop, for example, for loops in this case, okay, to analyze it, you always go inside out, because if you want to know how much time it takes for the outer loop, there's some echoes going on. So let's just make sure that everyone has already muted yourself, because there's some echoes. Let's see. Because if you want to know how much time an outer loop takes, you have to know how much it takes inside. Okay, so you always go inside out, no matter how many layers you have. Okay? The second thing that we have to be careful, it's not that if you see nested loops, then always each nested loop gives you time n. Okay, so for example, we saw this example last time that for this nested loop, the inner one, when you look at you go inside out. When you look at the inner loop, it only runs in constant number of iterations, because it goes from n to n plus 10. So there are only 10 iterations. So the inner loop only takes constant time, and the outer loop takes n time. That's why the total time complexity is linear order. Okay. Now, for the following one, it looks very similar to this one. However, if you look at the inner loop, so this print command still takes constant time, but this now takes linear time, because it's the number of iterations is basically 2n minus 10 minus n, which is n minus 10. Okay, so the total time complexity becomes on the order of n times n minus 10, which is of quadratic complexity. Okay, so we have to, in general, you have to look into the loops and figure out how many iterations it runs. Okay, this becomes even more important when you have a loop which is not a for loop, but it's a while loop. Okay, and we're going to see more examples at the end of today's class. All right. Here's another example of having a nested loop. Okay, so suppose that you are given n sticks, and you're supposed to design an algorithm to compute the tallest pole that you can make by stacking 2 sticks together. Okay, so you're given n sticks together with their lengths, and you need to pick 2 out of them and put them together and return the one that gives you the tallest one, the longest in length. Okay, again, when we're given the problem, okay, the first thing you ask yourself, what is the most simple, the most straightforward way that I'm going to solve this problem? Okay, what is that algorithm? Well, we have n sticks, and we need to pick 2 out of it to make a pole. So let's just try all combinations. Okay, so the first idea to design this algorithm is the following. Okay, so let's take a look. So we, let's see, where's the annotate? So the inner loop, so what we see here is that I'm simply going to enumerate all possible I and j, okay, inside. You have n sticks, I'm going to take all possible combinations, okay? So the first choice can go from 1 to n, and the second choice, because you don't want to repeat, can go from the I plus 1 to n. Okay, so this is just you take all possible combinations. And then for each of the combination, you just say that, okay, if you take the I stick and the j stick and put them together, what is the current height? Okay, meanwhile, you maintain the max height you have seen so far. Okay, if this height is bigger than the max height that you've seen so far, that means that you found a better one. Then you replace the max height you see so far with the current one, and then repeat till you try all combinations. Okay, it's a very simple algorithm. So what is this time complexity? Well, as we said that when you're given this nested loop, we always go inside out, okay? So you have two for loop at the lines 3 and 4, okay? So we look at the inner loop first. Well, the inner loop, each time when you are in one iteration of inner loop, you execute lines 5 to 7. That's easy. That only takes time constant, okay? The question is that how many times does this inner body will have to run, okay? So this one is a little bit trickier than the previous one. So what you can ask is that, let's fix the outer loop, okay, for each iteration of the outer loop. Because what we see is that the number of times the inner loop runs depends on I, and I is changing. Okay, so now you ask that if we fix the outer loop, how much time does the inner loop run? Okay, and for this, you will see that, okay, for the first iteration, I equal to 0. Okay, and the inner loop goes from 1 to n, which means that it's going to run n minus 1 time. Okay, then for the second outer loop iteration, I equal to 1. The inner loop goes from n minus 2 because it always goes from the inner loop goes from I plus 1 to n. Okay, and so on. And when you are in the last run, for the iteration number n, I in that case equal to n minus 1. In this case, the inner loop runs n minus I plus 1, which is basically 0 times. Okay, so this is what we have. Okay, now after you go once through this thought process, you realize really what we're saying is the following. What we're saying is that for the case iteration of the outer loop, okay, we know that for the case iteration of the outer loop, what happens is that I in this case equal to k minus 1 because the indices of the array goes from 0 onwards, okay, while the iteration goes from 1 to onwards, okay, and this inner for loop runs in the number of iterations is m minus I plus 1, which is m minus k, okay, and inside lines 5 to 7 takes constant time. That's why that for the case iteration of the outer loop, the inner loop takes c times n minus k time, okay, because it runs n minus k iterations and each one takes only constant time. Okay, so this is for the case iteration, but then the total time complexity is you basically sum up all this cost for each of the outer loop iteration. Okay, so what we have is the following. So basically in the end, the total cost incurred by lines 5 to 7, the inner body is basically, I ignored the constant c here, basically n minus 1 that comes from the first outer loop iteration, and minus 2, and so on till the last iteration. Okay, this gives us the same as 1. So this is 0, this is 1, and so on. As you can see that this is simply the arithmetic series in the inverse order. So it's basically 0 plus 1 plus 2 and so on. Okay, all the way till n minus 1. Okay, what is the sum of this? Well, the sum of this is simply, this is an arithmetic series. What we have is that this equal to n minus 1 times n divided by 2. okay? And if I write this one out, this is n squared over 2 minus n over 2, okay? So this is our time complexity. So, oops. Now, remember we also said that I don't want to have all this constant and the lower order terms hanging. So we simplify. We have t of n equal to n over, which is, we only keep the highest order and ignore the constants. We have the following. So this algorithm also runs in quadratic running time, okay? Again, I know that we haven't introduced this big theta notation formally, which we're going to do in 5 minutes, but this is intuitively, this will keep the growth, the dominating factor, okay? All right. And another way, in fact, to see this without going through, for the simple algorithm, without going through this inner and outer loop analysis, is that we recognize that what the algorithm is doing essentially is to choose all possible pairs, all possible combinations from n sticks, from the n objects, okay? And for each of such choice, we only spend constant time to figure out what to do to compute its length and so on. That's the body, line 5 to 7, okay? So as such, the total number of options, choices we have to go through is n choose 2, which is on the order of quadratic, and each one only take constant time. That's why the final time is quadratic order, okay? All right, but of course that I went through this example very fast because I didn't want you to think about it. For the simple problem, for this specific problem of finding the tallest pole, you can do much better than this quadratic running time. You can actually solve it in linear time, and that will be an exercise for you offline, okay? Writing linear time algorithm for this problem. Okay, so this is just some first examples to show that given when we see one common type of algorithm which has nested loop structure, how we analyze this time complexity. But now we've seen so far. Hold on, let me figure out why I have this feedback today. This echo. Let's see, put this further away. Okay, is this better? Is this better? Yes, I think now it's better. Okay. All right. So we've seen some different examples, different algorithms, and some of them, in the end, we have time complexity, which is order of n, we said. The others is order of n squared, okay? And we mentioned that, so what this notation really intuitively means is that this time complexity grows like n, and big theta of n squared means that the time complexity grows like n squared, okay? And the reason that we're happy with this level of abstraction is that this is sufficient to tell us how fast the algorithm grows as n increase, okay? And then naturally, if I give you this linear time algorithm and the quadratic time algorithm, you recognize that the linear time algorithm is much more efficient potentially than the quadratic one, because as the input size n grows, we know that the linear algorithm grows like this. Okay, so that's this is the function f of n equal to n. Okay, while the quadratic time algorithm, we know that if the value is 1, then it's, let me change the color, then the function is 1, but if the value is 2, then we go to 4. So the quadratic time algorithm goes like this, which grows much as n become larger and larger. So as n become bigger and bigger, we see that the n squared is much bigger than n. Okay, so okay, so just to give you some ideas that even though it looks the difference is not large when it's n squared, but in practice, this can make a significant difference, okay? So imagine that you have an algorithm that runs on 100 points, that's your input size, 1000 input size, it runs in 5 seconds. Okay, now your input has 100,000 number of points, which is 100 times the previous one. Okay, if your algorithm has a linear growth, that means that your the time complexity grows linearly, which is 5 times 100, which gives you 500, which gives you 500 seconds as the running time. Okay, while if your algorithm is quadratic growth, that means that if your time complexity should be 5 times 100 squared, which now give you 50,000 seconds time complexity. So the difference now, when you run on 100,000 number of points, is basically between 8 minutes and 14 hours. Okay, so even though that it sounds like it's just a factor of n difference, but in practice, this can make huge differences. Okay. All right. Now here are some of the common growth rate that you often see in time complexity. Okay, if it's growth order of 1, essentially means that the algorithm runs in constant time. Okay, and the log n, this is a logarithmic running time. And again, just to remind you that log base a n essentially is the quantity such that given a, if you raise it to this power, you get n back. Okay, so in other words, imagine that we have the standard log 2. Suppose log n base 2 is k. What does this mean? This means that if you multiply 2 k times, then you get n back. Okay, so this is the meaning of logarithm. Okay, and the linear is the standard linear order, and you can a lot of algorithms we're going to see later in this class going to have time complexity of the form n log n, and this log n actually comes naturally, especially when you have some recursive algorithm, which we'll see one example in the sorting next time. And quadratic algorithm is n squared, and if the time complexity is on the order of n cubed, that's cubic algorithm. And you can have a very inefficient algorithm like the one we saw last time for a naive algorithm to tackle the clustering problem that takes exponential running time. Okay, so this is just some common growth rate. All right, so finally, with all this description, we're kind of now ready to introduce what do we precisely mean by having this big theta notation. What does it mean that on the order of, say, linear or quadratic? Okay. All right. We already seen that using this big theta notation, it allows us to ignore unnecessary details about your time complexity so that we can focus on the dominating terms of growth. Okay, so whether your algorithm is n or it's n minus 1, n minus 2, it's grow really in the same rate. Okay, so the advantage of this notation is that it's now, once we write, we write the time complexity this way, it's easier to quickly recognize what is the time complexity of your algorithm and to compare the time complexity of different algorithms. Okay. Of course, that we have to define what exactly we are ignoring in using this big theta notation. Okay. Now, intuitively, I already used the term. I say, okay, big theta of n means that in the same order, in the linear order. Okay, or we say that this roughly means that your algorithm grows like n. Okay, so what you intuitively can think that big theta means the same, although up to this constants and the lower orders that we're ignoring. Okay, to define this precisely, instead of directly introducing big theta notation, I'm actually going to first introduce two other notations, the so-called big O and the big omega notation. Okay, again, using analogy, you can think that big theta means that your time complexity is in the same order of this function. Okay, it's like equality. Okay, and the big O that we're going to describe shortly means that is like smaller than or equal to, means that it's at most this function. It grows at most in this rate, okay? While big omega means that it grows at least at this rate. So intuitively, you could think of big O to be smaller than or equal to, it's like at most this, okay, time complexity. And big omega is intuitively bigger than or equal to, okay? And the big zeta that we have been using so far means that both big O and big omega, namely, they actually have to be equal, they're of the same order, okay? So big O is at most of this order, big omega is at least of this order, and the big zeta is of this order, equal, okay? All right, so more precisely, what do we have? Okay, we're going to look at these notations, but we're going to look at examples shortly, okay? So it's just, we say that a function f of n is in big O notation of another function g of n, okay? If there are, it's very important that if there are positive constants c such that, oops, this should be f of n, such that f of n is always bounded from above by c times g of n for n large enough, okay? So what this condition is saying that for n large enough, this following inequality has to hold. And this inequality is just saying that f of n intuitively is smaller than g of n, but allow a constant factor there, okay? So the more formal way actually to write this is that we write that fn is in the big O of g of n, okay? However, very often people simply merely write this equality, okay? So I will use the equality most of the time, but sometimes I may also use this notation here, okay? Again, what this big O notation means is that f of n is basically grows at most in the order of g of n up to some constant. That's what it's saying, okay? And we have this condition because we want to, when n is very small, we don't care so much, okay? We want to see how fast is your time complexity when for large data sets as n grows bigger and bigger, okay? So we, like in this case, when n is small, the two functions may not have a clear relation, but then as n become larger, okay, then we see that g of n is always higher than f of n after, up to a constant, basically, okay? So again, intuitively, you can think this big O as smaller than or equal to, but up to a constant, okay? So this is what we write here. Okay, so f of n grows at most as fast as g of n up to some multiplicative constant. Okay, and we also say that g of n is asymptotic upper bound for f of n in this case, because f of n is bounded from above by g of n. Is smaller than or equal to. All right, so let's look at some examples. So let's first look at the first one. The left-hand side is our f of n, okay? And this is our g of n, okay? Now, intuitively, it's easy to convince ourselves that, well, the left-hand side kind of the dominating factor is n cubed. So its growth is bounded from above by a cubic function, okay? But if I ask you to prove this using the previous formal definition, how do we do that? Well, to prove this, we note that we just need to establish that there exists some constant such that for n large enough, f of n is almost smaller than c times g of n, then we're done, okay? So for this particular case, what do we do? Well, we have that f of n equal to n cubed minus 3n squared plus 5m minus 1. This clearly is smaller than, I just want to show that it's bounded from above by something times n cubed, right? And to do that, I want to convert all this lower order term to n cubed, okay? So this is smaller than n cubed. And this is minus 3n squared, that's positive. I can just ignore it, okay? So, which is further smaller than n cubed plus 5n cubed, because clearly 5n is smaller than 5n cubed, right? So I don't even have to be tight. I can just do as long as. Now, what do we see? We see that f of n is smaller than 6 times n cubed, which is g of n. Okay, and this actually holds for any positive n. Okay, as such, by definition, we have that f of n is in big O of g of n. Sorry, in this case, I should write. In this case, f of n is defined as g of n is n cubed. Okay, because in this case, the constant in the previous definition is 6. Okay, so that's how we prove that this is in the big N of big O of g n cubed. So the second example is similar. Okay, so to prove that this is in the big O of n squared, we say that, okay, f of n equal to 5n squared plus 6 square root of n plus 8. I don't, as long as I can find, our goal is to find that this is smaller than some constant times n squared. That's our goal, okay? And this needs to be a constant. Now, this constant, I don't even care what that constant is. It can be 100, 1,000, 10,000, as long as it's a constant. Okay, so I can be pretty relaxed when I try to bound it. In this particular case, I can simply say that, okay, this is 5n squared, 6 times square root of n. Square root of n clearly is smaller than or equal to n squared, right? So this is smaller than 5n squared plus 6 times n squared. And 8 is clearly smaller than 8n squared. I'm enlarging it, right? So this gives us that the whole thing is smaller than 5 plus 6 plus 8, which is, that's confusing. 19 n squared. Okay, I don't have to be tight. Clearly, my bound, this constant can be made better, okay? But we don't care because we just need to establish there exists a constant, in this case, 19, okay? Such that f of n is always smaller than 19 times g of n, okay? Now, once we establish this, we say that by definition of big O notation, we have okay, this is actually for any n bigger than 1. Okay, so in this case, we'll just pick n0 to be 1. Okay, so that's it. So it's quite intuitive, but I'm writing this down. In general, when you look at this functions, you immediately recognize the first one is a cubic function, the second one is a quadratic function. But this is what I'm writing here is that, especially like in your homework, if I ask you to prove that this is the case, this is you have to go back to the definition and then use the definition to prove, which means that you have to establish that relation, this inequality, finding a constant that make it hold. Okay. All right. Questions? Okay. All right. So now let's look at some more examples and without proving it. Okay. So I'm going to ask you for each of this case whether what I'm writing here, the relation holds or not. Okay. All right. The first one, what do you think? Is this one correct? You can just type into the chat or you can just say it, unmute yourself and say it. So remember that the big O notation basically says that is this one intuitively bounded by some constant times the right-hand side for n large enough, okay? So we look at this has the square root of a function inside, but the function inside we recognize the dominating term intuitively is n cubed. Okay, the remainder lower order term can all be written as they're all smaller than the say 7n squared smaller than 7 times n cubed and so on. Okay, so dominating term here is n cubed, and then I need to take the square root of that. Okay, that means that what we have is n to the power of 3 over 2. Okay, which is clearly smaller than n squared. As such, this is correct. Okay, now by the same argument, we already said that this is actually dominating term is n cubed. So this is actually smaller than some constant times n cubed. Take the square root, which is n to the power of 3/2, which is 1.5. So this is also true. Okay, now in fact, let me just write it here. If I have to prove this, let's prove the second one. Okay. So f of n equal to square root 6n cubed plus 7n squared plus 3n, which is smaller than 6n cubed plus 7n cubed plus 3n cubed, which is the same as 16n cubed, which means that this is the 4 times n 1.5, and this is g of n. Okay, as such, by definition, we have that this inequality holds. Okay, I'm skipping the writing all the details out. Okay, so you just want to show that the left-hand side is always smaller than some constant times the right-hand side for some constant. Just need to establish that. Okay, now the reason I'm also giving you the first example is that you see what the big O notation is saying is that as long as it's smaller than some constant times another function, then it's basically smaller than or equal to. Okay, so if it works, if the second inequality, relation holds, then clearly since n squared is bigger than n to the power of 1.5, okay, then clearly the first one also holds. Okay, and they don't have to be tied. So big O doesn't mean that they're of the same order. It's just saying that I am growing as fast as, at most, as fast as you. Okay, all right. Okay, let's look at this one. What do you think? Well, on the left-hand side, we have n, but then divided by a function, which is an increasing function of n, right? So clearly, n over log n is strictly actually smaller than n, okay? That means that this is in the big O of n, okay? Again, big O means smaller than or equal to, which means the left-hand side function can be much smaller than the right-hand side function, okay, which is like in this case, okay? All right, how about this? Is this correct? Does this relation hold?
Would it be no?
Why?
Because there are like coefficients of the big O function that would be smaller than the left-hand side.
Well, if we, okay, let's do this a little bit more formally to see. Let's set f of n equal to 100 n log n, right? Now, if this relation holds, that means that if we can find some function, some constant, such that this always holds, then we're done, right? Can you give me, does such constant exist? In fact, we can just take 100 here. So by definition, in fact, f of n is, this is, right? So if this is g of n, this is f of n, then clearly f of n is smaller than 100 times g of n, right? As such, they do have the big O relation. And I'm using this example to make the point that when we say that f of n is in the big O of g of n, different from the standard smaller than or equal to, here is smaller than or equal to up to a constant. Okay, so the f of n may not be always smaller than g of n. However, if you can find a constant so that f of n is always smaller than the constant times g of n, then you are fine. So that's the difference between when I use the analogy saying that big O means smaller than or equal to. So here is smaller than or equal to up to a constant factor. Does it make sense?
Yeah, thank you.
Okay, so so this is also, so basically so far all of them are correct. Okay, how about the next one? So here, f of n is n log n, and the g of n is n. And we ask ourselves the question, can I find some constant such that C such that for n large enough, f of n, which is n log n, is always smaller than some C times n, right? So this is what we're asking, right? So we're asking whether there's such constant exists. Okay, what do you think? Does such a constant exist? Well, what we notice is that you see f of n, as n grows bigger, the difference between f of n and g of n is actually this factor log n, okay? But the log n itself is an increasing function that goes to infinity as n gets bigger and bigger, right? Which means that you can never find a fixed constant c to be bigger than log n, because log n itself grows to infinity as n becomes bigger, okay? So the function for n log n essentially looks like this, which means that as n become larger, the difference between f of n and g of n become bigger and bigger, cannot be bounded by any constant. Okay, so such a c does not exist, and this relation does not hold. Okay, which is naturally so, because this is just the growth in linear. Here is linear, but multiplied by another increasing function. Okay, so this is not true. Question on this? Okay, we're going to see more examples, and then hopefully they become things start to make more sense. All right, let's look at the last one. What do you think? So this is a logarithm function, but with different bases. One is base 2, one is base 10. So maybe here's the hint. Okay, what we know that for logarithm function, we have the following formula. Okay, we know that log m base a equal to, you can actually change the base to a different base b divided over. Okay, so this is a change of base formula to help you to convert the basis of logarithm function to different bases. Okay, so now apply this. What do we have? So right now I don't immediately see the relation between f of n and the g of n because they are of different bases, right? So for me to relate them, I want to know, our question is that is f of n smaller than some constant times g of n? That's our question, right? So I want to find whether there's exists a constant to make this true or not, okay? And right now, f of n is log m base 2, while g of n is log m base 10. For me to be able to relate them, it would be nice if I can change this one, the base of the f of n, to also base of 10 log m base 10, okay? So that they become more comparable, okay? So apply this change of base formula. So what we have is the following: f of n equal to log m base 2. Then I apply the formula that's the same as log m base 10 divided over log 2 base 10. Okay, and this is the in fact, it doesn't even matter. Okay, what we have is that now we rewrite f of n to be g of n times some constant. Okay, I don't need to know the precise quantity of this, but this is a constant, which means that this is smaller than c times log 10n, where c equal to. Okay, which by definition, this is g of n, remember? So by definition, we found that there exists a constant such that f of n is actually equal to, in this case, but equal is the same as smaller than equal to, smaller than constant times g of n. Okay, so because of this, we conclude that indeed log of 2n is in the big O of log of 10n. Questions on this? Okay, now, in fact, here, the precise value of 2 and 10 are not even important, okay? What we see is that basically, in fact, any constant here, okay, if the quantity is bigger than 1, then you can use the same trick and argue that, so this can be any constant A, and this base can be any constant B. This relation will then hold. Okay, because once you apply the change of base formula, then you can change a logarithmic function from one base to another one, multiplying just by a constant. Okay, that's why this relation holds. All right, questions? Okay, I'm going to move forward. All right, so this is the some examples of big O notation. So here's another equivalent definition of big O notation in some sense. That's very often it's actually easier for you to apply. Okay, so suppose you want to understand the relation between f of n and the g of n. Okay, now take the ratio of them. Look at this function. Okay, and assume that as n goes to infinity, the ratio of this function exists. Okay, if the limit exists, then it turns out simply by definition, okay, if it exists, if the limit is smaller, is bounded from above by any positive constant, then f of n is in the big O of g of n. Okay, this basically follows from the definition. But this form is sometimes easier to use. Okay, so before I talk about the corollary, let's actually look at one example. I'm coming back to this page. So for example, now let's look at this example. I ask you that, is this true? Okay, So let's apply what we just said previously. In fact, let's look at a slightly different, an even easier one. Okay, so let's say I ask you, is the following true? Okay, so what that means is that in this case, f of n is n squared and g of n is n to the power of 100. Okay, so let's take the ratio of f of n divided by g of n, okay, and then look at its limit. What is the ratio? The ratio is n squared divided by n to the power of 100, and then n goes to infinity. And this is the same as limit 1 divided by n to the power of 98, and n goes to infinity, right? So what is the limit? What is the limit of 1 over n to the power of 98? As n becomes larger and larger, what does this go to? As n become larger and larger, this become larger and larger, right? And this goes to infinity, which means that 1 over this goes to 0. So the limit of this ratio goes to 0 in the infinity. Okay, what does that mean? If the limit goes to 0, then clearly it's smaller than some constant, right? You can pick any constant. 0 is clearly smaller than, say, 1. In this case, actually, any constant works. Okay, now using the previous result, we proved that as such, we know that holds. Okay, so this is what we have. Okay, so using the previous limit argument. Okay, all right. So basically, in general, when you are given some functions that you want to figure out this relation, you can either use the definition we introduced, or you can use this lemma, this equivalent definition in some sense. Okay, all right. The implication of this definition is actually, we already said that if the limit becomes 0, what this means is that clearly you can find a positive constant so that it's smaller than a constant. If it's smaller is equal to 0, clearly it's smaller than any constant. Okay, and as such, in this case, fn of big O of g of n definitely hold. Okay, the converse is not necessarily true. Okay, another implication is that suppose you compute the limit, but the limit is you compute the limit, and the limit is infinity. Okay, what does this mean? The limit goes to infinity means that you cannot find any constant so that the limit is smaller than the constant, because the limit goes above the constant, grows faster than constant. Okay, what this means is that in this case, this relation definitely does not hold. Okay, so this is just 2 special cases that's easier for us to sometimes recognize the relation between functions. Okay, so this 2. All right, let's look at some examples. So for example, does this first relation hold? What do you think? What if you apply both intuitively, or if you apply the limit trick that we just introduced? I'll give you 1 minute and let's see. Is n to the power of 100 bounded from above by n squared? Well, I mean, this function grows much faster than quadratic function. So intuitively, we know that this cannot be true. Okay, because I mean, this function, there's no constant to say that you can multiply on n squared to make n to the power 100 smaller than some constant time n squared. Okay, and to see this more formally, if I ask you to prove it, to see this more formally, you can just take the limit of f of n over g of n, which is n to the power of 100 over n to the power of square, which is limit n to the power of 98. As you can see that this is a polynomial function n, and as n goes to infinity, this quantity goes to infinity. So this gives me positive infinity. Okay? And as such, by this corollary, we know that this relation cannot hold because no such constant can exist. Okay? All right. By the same argument, you can convince yourself that this, using the limit argument, you can convince yourself that this is correct. Well, intuitively, this is also true. If you ignore the constant, log n grows much more slowly than n, because log n is that how many times do I have to multiply 10, and this is base 10, in order to get n, which is quantity much smaller than n, okay? And so both of this are true. How about this? Well, sometimes when it's not obvious, we again resort to this limit trick, okay? So we can do limit of n to the power 100 to 2 to the n. Okay, it turned out, oops. Now it turned out that this is something called a polynomial function, and this is exponential function. Okay, as n becomes larger and larger, exponential function always grows faster than polynomial function as long as the base of the exponential function is bigger than 1. Okay, so in the limit, this is much bigger than n to the power of 100. So exponential grows much faster. So the limit of this is 0. Okay, since the limit is 0, it's clearly smaller than any constant you pick. Okay, which means that by this first corollary, we have that this relation indeed holds. Okay, so this is also true. Okay. And for the last one, if we use the same trick, we get that this is the same as which means that this is a value which is smaller than 1, and then when I raise the to exponential to power of n, it gets smaller and smaller. So then the limit, this also becomes 0. As such, this is smaller than any constant that you pick, so this is also true. Okay, so I'm having these few examples. Number 1, to show that very often this limit trick using the limit of fn over g of n makes it easier for you to see whether the one function is bounded from above by the other function or not. Okay. Number 2, as we also see that what we have here is that polynomial function intuitively is bounded from above by exponential function, because as n becomes large, exponential function always grows faster. Okay, and if they're all polynomial function, then it depends on what's your exponent, of course. Okay. Yeah, sorry, this is wrong. This is the wrong direction. The first one is wrong. The remainder are all correct. Okay. Questions? Okay, so that is a big O notation, which intuitively says that function f is smaller than some constant times function g. Okay, so function f grows as fast as g up to a constant, basically. So the big omega notation that we're introducing now is basically the other direction. It says that the function f is at least the g of n with multiplied by a appropriate constant. Okay, in other words, we say that f of n is in the big O of g of n. Again, if there exists a positive constant such that for n, this just means that for n, this just means that for n large enough. Okay, so for n large enough, f of n is bigger than g of n, which you again allow some constant factor in front of it. Okay, so you want to ignore the constant factor. So after constant factor, f of n is always bigger than g of n. Okay, and in this case, we say that g of n is an asymptotic lower bound than f of n because f of n is bigger than it. So g of n is bounding f of n from below now. Okay, and intuitively, this means that f of n grows at least as fast as g of n up to a multiplicative constant. Okay. So from the point of view of a picture, so what this says is that when n is large enough, so when n is bigger than n0 means that when n is large enough, then the function, the curve of f of n is always above g of n times some constant. Okay, so that's the meaning of this. Okay, so as this means that f of n is bigger than c times g of n. Okay, all right. So let's look at another example and also prove this using the definition. It's similar to the previous one. Okay, how do we prove this? Well, intuitively, so f of n in this case is n cubed minus 3n squared plus 5m, and the g of n is n cubed. Okay, what do I want to do? We want to show that f of n essentially is bigger than some constant times g of n, right? We want to show that for n large enough, f of n is always bigger than g of n up to constant. We need to find this constant. If we can find this constant, then we're done, okay? So in this case, we have to relax in the opposite direction as before. So clearly, we can first ignore this 5n because that's positive. So this is bigger than n cubed minus 3n squared. Okay, but now this is a bit trickier because I cannot directly just throw this away because this is subtracting. Okay, however, intuitively, this is the lower order terms. What does it mean? This means that for n large enough, very soon we will have that this is smaller than, say, 1/2 of n cubed for n bigger than 6. Okay? Why? Because for n bigger than 6, we have that, so just to prove my statement. So for if n is bigger than 6, that means that n cubed is bigger than 6n squared. I'm just multiplying n squared on both sides, which means that 1/2 of n cubed is bigger than 3 times n squared. Okay, so this is a proof of the statement. Okay, so what we know is that for n bigger than 6, we have this is bigger than n cubed minus 1/2 of n cubed, which means that this is bigger than 1/2 of n cubed. So that's how we prove it. Okay, because then what did we say? We said that that means for n bigger than n squared equal to 6, we have that 1 of n bigger than 1/2 times g of n. And as such, by definition, we have this relation holds. Okay? Questions? So it's very similar to the previous proof, but here we have to use a little bit more work because we cannot just simply ignore this term. Okay? But intuitively, what's happening here is that you see for lower order term, that's why that you can still make the two, replace it by a higher order term with much smaller coefficients, basically. That's why the lower order term can be ignored. Okay. All right. Now, in practice, when we try to figure out the relations, again, the same limiting, using the limit, the same trick is very helpful. Okay. So an equivalent definition of big omega notation is that if this limit exists, then the limit Fn is bounded from below by g of n, namely Fn is in the big omega of g of n, if and only if this limit is bigger than some positive constant. This is very important that here has to be a positive constant. Okay, now the implication of this, corollary number 1, is that if the limit is positive infinity, clearly this is bigger than any positive constant you are going to pick. You can just pick c equal to 1. Okay, so if the limit is infinity, clearly this is bigger than 1. As such, in this case, f of n is in the big omega of g of n. So this is one of the special cases. Okay, another implication is that if the limit is actually 0, what does it mean? Well, this means that it's not possible to find any positive constant, so 0 is bigger than the positive constant, right? So that means that this cannot happen. We cannot find any c to make this hold. Okay, as such, this relation cannot hold. Okay, well, intuitively, if the limit is 0, if the limit of the ratio f of n over g of n is 0, what does it mean? That means that the g of n grows much faster than f of n. So how can it be that f of n is bigger than g of n? Okay, so it's not possible in that case. Okay, so these are very useful corollaries to help us to figure out the relation between the functions. Okay. All right, and here are some more examples. I will not go over all of them. Many of them can be done by similar tricks. And let's just look at a few of them. Okay. The first one, intuitively, the left-hand side essentially is a quadratic function, the dominating term. Okay, while the right-hand side is cubic function. So what do you think? Does this hold? Is quadratic function bounded from below by a cubic function? Well, intuitively, quadratic function grows slower than cubic function. So it's not possible that n squared is bigger than some constant times n cube. Okay, so n cube is much larger. So this is not true. And you can, this is much easier to, this is intuitive, but you can also prove this formally by using the limit of fn over g of n. Okay, and this, well, on the left-hand side is a quadratic function, which has the dominating term. The right-hand side is quadratic function. So clearly, this is bounded from below by n squared. Okay, so this is true. Okay. How about this one? Is the third relation true? So again, I'm using this example to show the same issue of a constant. So in this case, f of n is n squared. G of n is 100 times n squared. Okay, so we have that f of n equal to 1 over 100 times 100 n squared, which is that this is 1 over 100 times g of n. Okay, so 1 over 100 is smaller than 1. But we never said the constant cannot be smaller than 1. We just said that it has to be a positive constant. Okay, so as such, this is equal to this, which is also means that this is bigger than equal to. Which means that I can find a constant, which is 1 over 100, such that this relation holds. And as such, f of n is indeed bounded from below by g of n. Okay, so this is also correct. Okay, all right. I will leave yourself to figure out, to convince yourself of the remainder. So this one, the dominating term is n cubed inside the square root, which after taking square root is n to the power of 1.5. So this is also correct. And this one, you have an exponential function on the left and a polynomial function on the right. and exponential function intuitively grows much faster than polynomial function. As such, it's bigger than polynomial function when n is large enough. Okay, so this is also true. And you can prove this formula again using the limit of these two functions. Okay, and this is the opposite because the logarithmic function grows much slowly than linear function. So log n cannot be bigger than n for n large enough. So this is wrong. Okay, so I will write them, I'll mark them here, and as exercise, you can try to convince yourself of them offline. Okay. All right. Questions? Okay. Okay, so finally we're ready to put both of them together. Okay, so the big theta notation, we say that f of n is in the big theta of g of n if f of n is bounded both from above and below by g of n up to constant. Okay, again, all of this allows we have some constants. As long as you can find some constant, positive constants, C1 and C2, such that when n is large enough, f of n is sandwiched between different constant times g of n, then this two essentially is of the same order because their difference is only multiplicatively constant. Okay, so that's the meaning. And as you see from this definition, this part means that f of n is in the big O of g of n. And this part means that f of n is in the big omega of g of n. Okay, in other words, what I claim is that f of n is in big theta of g of n if and only if f of n is in big O of g of n and f of n is in big omega of g of n. This is like saying that two numbers a and b, a equal to b, if and only if a is both bigger than equal to b and a is smaller than equal to b. Okay, but the difference here for the function compared to the number case is that here the smaller than or bigger than and equal is up to constant. Okay, so that's the only difference. Okay, so this is like a bigger than or equal, and this is like smaller than and equal, and this means that they are kind of equal to each other up to constant. Okay, so from the illustration point of view, this means that when n is large enough, so here this is just means when n is large enough, when you look at f of n, it's both bounded from above by a constant times g of n, and also bounded from below by a constant times g of n. Okay, so fn is sandwiched between different constant factor times g of n. So they grow kind of at a similar rate up to constant. Okay. All right. And the similar to before, we have the same results when you look at the ratio of the f of n over g of n and look at its limit. Okay, so combine the two previous cases for big O and big omega together. Now we have that if you look at this ratio of fn over g of n, okay, if the limit goes to a quantity which is in between two constants, okay, then that means that f of n essentially and g of n are of the same order. So this is quite, in particular, let's actually look at this corollary. Okay, so if the limit of fn over g of n goes to a specific constant, okay, then that means that essentially this f of n and g of n only differ by a constant factor intuitively. Okay, so if the limit in the limit they only differ by a constant multiplicative factor, so they're of the same order, in which case implies that fn equal to big theta of g of n. Okay, so here are some more examples. In this case, when we look at this, the left-hand side, this intuitively we immediately see that, okay, this is of the dominating terms in Q, okay? As such, it must be the same as the same order as n cubed. Okay, so already intuitively, we already convinced ourselves. If I ask you, like in the homework, if I ask you to prove this, what do we need to do? We basically need to go back to the definition. Okay, so there are two ways to prove this. Let me just put both of the solution down. Both are valid in your homework. Okay, so the option, the first way is to use the original definition. You say that, okay, f of n equal to 2n cubed minus 3n squared, which is clearly smaller than 2n squared, which is 2 times g of n. So g of n is, okay, so this implies, because f of n is smaller than 2 times g of n, this implies that f of n is bounded from, oops, is bounded from above by g of n, smaller than or equal to, okay? Furthermore, f of n is bigger than, say, 2n cubed minus n cubed for n large enough. For example, this holds if n is bigger than 3. Okay, you can verify this is true for n bigger than 3. Okay, and which means that for n bigger than 3, we have f of n bigger than n cubed, which is constant c now is 1 times n cubed, which implies that f of n is also bounded from below by g of n. Okay, and putting 1 and 2 together, we have f of n equal to big theta of g of n. Okay, in other words, if I ask you to prove something, one function is in the big theta of the other function, you basically need to prove two sides. Namely, it's both bounded from above by the other function and also bounded from below. Okay, but of course, you can also use this limit trick that we just talked about. In fact, it's probably easier for many of the problems. So you can take the limit of the function 2n cubed minus 3n squared divide n cubed. Okay, this is simply the limit of f of n over g of n equal to. And then the limit of this, as we see that this is a low order term. So let me actually write it out. Minus 3 over n, right? Which is limit 2 over 3 minus 3 over n. And as we see, as n goes to infinity, 3 over n goes to 0. Okay, so the limit of this is simply 2 over 3. In other words, the limit of this f of n over g of n goes to a constant, which means that the two functions are of the same order. Okay, so in other words, using this corollary. Okay, so this implies that f of n is in the using corollary from previous slide. Okay, so both ways are valid ways to prove formally that these two functions have the same, have the big theta relation. Okay, all right. Okay, so here are some of the examples. Okay, now the first one, we can quickly convince ourselves that the dominating term is n squared. Clearly, that's in the same big theta of n squared. Okay, so this is correct. And here, the dominating term is n cubed inside the square root. And after you take the square root, that's basically n to the power of 1.5. Okay, so this two again is of the same order. Okay, how about this one? What do you think? How many of does any of you think this one is not correct? Well, here it looks a little bit misleading that we have n squared minus log n. But intuitively, what is the log n? That's a lower order term. That's much smaller than n squared, right? So essentially, n squared minus log n clearly, first the n squared minus log n is clearly smaller than n squared. So the upper bound we already have, the big O relation, okay? And because this is so small, we know that for n large enough, this is clearly bigger than, say, because for n large enough, log n is smaller than n squared over 2, okay? So for n large enough, we have okay? This means that we also have the lower bound relation. Okay, combine this and this, we show that they have the big theta relation. Okay, so that's what we have. All right. So so far this is correct, and this is not. Okay, and now between 3 to the power of n and 2 to the power of n. Okay, so I'll leave this to yourself to convince yourself to prove this is actually not true. Okay, so I'll leave this as an exercise for yourself to show later that this is not true. Okay, all right, the last one actually earlier when we did the change of base formula, we have that log n actually equal to log n over 2 log. Okay, which means that so remember this is f of n and this is g of n, which means that f and g of n only differ by a constant factor. Okay, which means that clearly they're of the same order. So this is correct. Okay, so this one I'll leave it for yourself to do it offline. Okay, all right. Okay, so let me just summarize this part. What we saw here is that the big O, big omega, and the big theta, these are all precise language for us to be able to compare time complex functions. Here, in the future, of course, in this class, these functions f of n, g of n, they are going to be time complexity of our algorithms. Okay, so this is a way to compare functions. Okay, when you compare them intuitively, you want to ignore the constant factors. You also want to ignore lower order terms. Okay, and the way we achieve this is that we say, okay, I say that the one function, I'm sorry that in all of this here, it should be n instead of h. Okay, I'll correct the slide later. You basically want to say that, okay, I want to say a function f is smaller than function g, okay? But then I want to relax it to allow a constant factor up to constant. That's why you say that f of n is in the big O of g of n as long as f of n is always smaller than g of n up to a constant. Okay, so this means, so big O means smaller than equal to up to a constant. Same for big omega, it means that f of n is always bigger than g of n up to a constant. Okay, so this is the big omega notation. Okay, and big theta means that they're kind of tight. They're both, f of n is both smaller than constant 1 times g of n and also bigger than constant 2 times g of n. So intuitively, they only differ by constant factor. Okay, which means that they're of the same scale. So in this case, we consider the two functions to be asymptotically tight. They are asymptotically the same as each other. Okay. All right. So I'll stop here. Now in the slides, oops, I have some remainder examples on analyzing nested loops. Okay. What I will do is that right now I didn't fill them in. What I'll do is that I'll add the solutions here to the slides so that you can take a look later to know the answer of this. Okay, and I think some of this would also be covered in the discussion session. And in your homework, there will be some problems which involves a while loop. Okay, so that's all for this class. Again, a reminder that your first homework is actually already out, available on the course website, and you're encouraged to use the LaTeX to solve the problem, to write your homework. Okay. All right, that's all for today's class.
Thank you.